we begin with a definition, Darboux continuity. Let f from some closed interval a b to R be a function. We say f is Darboux continuous if for all c comma d in this closed interval a b, f has the intermediate value property IVP in the closed interval CD. That means if you take 2 points C and D in AB, look at f of C and f of D, assume for concreteness that f of C is less than f of D, then all values in between f of C and f of D will be taken by f as you go along the interval CD. Okay, so we already know that a continuous function is automatically Darboux continuity. We have just proved that. But the converse is not true, as the function sine 1 by x shows. The function sine 1 by x when x is not 0 and 0 when x equal to 0 is Darboux continuous. It is Darboux continuous, but it is not continuous at the origin because it oscillates wildly. So Darboux continuity does not imply continuity. You will later see that derivatives of functions are Darboux continuous. They may not be continuous, but they will certainly be Darboux continuous. They will have the intermediate value property. Now, is there some collection of Darboux continuous functions which are automatically continuous, in the sense that can you show that Darboux continuity plus something else will at least give you continuity? Yes. For that I need a definition. Let f from AB to R be a function. We say f is strictly increasing if x less than y implies f of x less than f of y for all xy coming from AB. So the definition is fairly straightforward. Just a remark. Similarly, we can define strictly decreasing. We will see more about these functions when we talk about derivatives, especially when we interpret the sign of the second derivative. So the following theorem is really interesting. Theorem: let f from AB to R be a strictly increasing function that is Darboux continuous. Then f is continuous. Okay, how do we prove this? The proof is not at all hard. We have all the tools at our disposal and we will not be using any of them to show this. So let x be a point in AB. Okay. First let me take the special case when it's an interior point. The argument for the endpoints is going to be left as an exercise to you. So let x be in AB. Okay. Fix epsilon greater than 0. Okay. Then observe that f of a is strictly less than f of x is strictly less than f of b. Right? Because f is Darboux continuous, that means there exists x1 such that f of x1 is equal to f of x minus epsilon, and f of x1 equal to f of x minus epsilon, and there exists x2 such that f of x2 is equal to f of x plus epsilon, x1 and x2 coming from this closed interval AB. Okay, so fix epsilon greater than 0 such that epsilon is less than minimum of f of x minus a comma f of b f of x minus f of a and f of b minus f of a. F of x. So I'm just going to choose epsilon so small that this f of x minus epsilon and f of x plus epsilon lie within f of a, f of b. If I choose epsilon to be less than minimum of f of x minus f of a, comma f of b minus f of x, this will be true. Okay. Not only does there exist x1 and x2 such that this happens, but these points are unique. These points are unique. These points are unique. Why? Because f is strictly increasing. F is strictly increasing. Because of that, these points are unique. Okay. Now let delta be equal to minimum of x2 minus x and x minus x1. Okay. Fine. Then this choice of delta works in the epsilon delta definition. Why does it work? Well, because x minus delta comma x plus delta, if you look at this interval, this is going to be contained in the interval x2 it's going to be contained in the interval x1 x2, right? It's going to be contained in the interval x1 x2, and at this point it is f of x plus epsilon, and at this point you get f of x minus epsilon, right? F, when you apply f, right? By strictly increasing property, that means f of x minus delta comma x plus delta, this entire interval has to be contained in f of x minus epsilon, f of x plus epsilon, in fact open. Okay, which is nothing but the definition, which is nothing but epsilon delta definition. Hence proved. Okay. Remark. Similar result is true for strictly decreasing functions. So I leave it to you to formulate and prove this result. It will be exactly the same thing. This is a course on real analysis, and you have just watched the module on Darboux continuity and monotone functions.